C# and AI Masterclass by Edgar Milvis Volume 9, Chapter 7. Let's discuss Chapter 7, Loading GGUF Models, Llama 3, Phi-3. Moving on to Theoretical Foundations. The theoretical foundation of loading GGUF models, Llama 3, Phi-3, within a .NET environment via the ONNX Runtime GenAI library rests on the intersection of efficient model serialization, memory management strategies for edge devices, and the abstraction of complex tensor operations. To understand this deeply, we must move beyond simple file I/O and explore the architecture of quantized inference. Now, let's talk about the GGUF format, a library card catalog for neural networks. Imagine a massive public library. In the early days of AI, the analog era, books, model weights, were stored on loose-leaf paper. To find a specific sentence, you had to scan every page linearly. This was inefficient and required massive storage, high-precision FP32 weights. GGUF, GPT-generated unified format, is the library's modern digital card catalog system. It is not just a container, it is a structured serialization format designed specifically for the constraints of local inference. Why GGUF? In previous chapters, we discussed the challenges of deploying models on edge devices, Book 8, Edge AI. Edge devices have limited RAM and compute power. Storing a 7 billion parameter model in standard FP32, 32-bit floating point, requires approximately 28 gigabytes of memory. This is impossible on most consumer hardware. GGUF solves this by supporting quantization, compressing weights into lower precision formats, like int4, q4_k_m, without significant loss of reasoning capability. The structure of GGUF, a GGUF file is essentially a binary blob with a strict header structure. It contains 1. General metadata, model name, architecture, e.g., Llama, quantization version. 2. Tensor data, the actual weights, parameters, of the neural network, stored as arrays of floating point or integer values. 3. Token vocabulary, the dictionary mapping text tokens, like Apple, to integer IDs. Analogy, the compressed recipe book. Think of a neural network as a complex recipe for baking a cake, generating text. FP32 model, a recipe where ingredients are measured to the microgram, e.g., 125.345 g of flour. Accurate, but requires a precision scale, high VRAM, and takes a long time to measure, slow compute. GGUF, quantized, a recipe where ingredients are rounded to the nearest gram, e.g., 125 g of flour. The cake tastes 99% the same, but you can use a simple scoop, low VRAM, and measure instantly, fast inference. When we load a GGUF file in C#, we are not just reading bytes. We are instructing the runtime to interpret these compressed recipes and map them into the mathematical structure of the neural network layers. Now, let's explore the ONNX Runtime GenAI library, the universal translator. While GGUF is the storage format, we need an engine to execute the mathematical operations defined by those weights. This is where the ONNX Runtime GenAI library comes into play. In Book 6, we discussed the ONNX format as an open standard for interoperability. However, standard ONNX runtime is designed for general-purpose tensor operations. ORT GenAI is a specialized wrapper built on top of the core runtime, specifically optimized for generative AI models, like Llama and Phi-3. The abstraction layer, in C#, we interact with the model through high-level abstractions provided by the Microsoft.ml.ONNX Runtime GenAI namespace. The library handles the complexity of 1. Graph execution, mapping the GGUF tensors to the ONNX computational graph. 2. KV cache management, handling the key-value cache for autoregressive generation, crucial for maintaining context in long conversations. 3. Beam search and sampling, managing the probabilistic selection of the next token. Why C# and ONNX? C# is a strongly typed, memory-safe language. When dealing with large binary files, GGUF, and unmanaged memory, tensor buffers, C# provides robust mechanisms to prevent memory leaks, a critical requirement for edge devices that run continuously. The ONNX Runtime GenAI library bridges the gap between the unmanaged world of C++, where the core inference engine lives, and the managed world of C#. Turning our attention to the loading mechanism, from disk to memory. The theoretical process of loading a GGUF model involves three distinct stages: deserialization, memory mapping, and graph construction. Now, let's talk about 1. Deserialization and header parsing. When the C# application initiates a load, the first step is to read the GGUF header. This is a binary read operation. Magic number, the first 4 bytes identify the file as a GGUF file, usually 0x47475546. Versioning. The runtime checks the version to ensure compatibility with the ONNX GenAI adapter. Metadata. Key value pairs are read. For example, general.architecture, Llama, tells the loader to instantiate a Llama-specific graph structure. Moving on to 2. Memory mapping, the edge constraint. In a desktop environment, we might load the entire 4 GB model into RAM using file.readAllBytes. On an edge device, like a Raspberry Pi or an industrial IoT gateway, this is fatal. It causes swapping, using slow disk space as RAM, destroying inference speed. Theoretical solution, memory mapped files, MMF, modern C# supports memory mapped file. This allows us to treat a file on disk as if it were entirely in memory. The OS handles paging, loading only the parts of the model currently needed by the CPU/GPU into physical RAM. Analogy, think of MMF as a lazy loader for a movie. Instead of downloading the entire 4K movie before watching, you stream it. The OS fetches the next scene, tensor block, just before the processor needs it. Now, let's talk about 3. Graph construction and quantization handling. Once the weights are accessible, via MMF or direct load, the ONNX GenAI runtime constructs the computational graph. This is where the magic of quantization happens. If you load a Q4_K_M quantized Llama 3 model, the weights are stored as 4-bit integers. However, the neural network operations, matrix multiplications, require specific data types. To quantization, the runtime applies scaling factors, stored in the GGUF header, to convert 4-bit integers back to floating point values on the fly during computation. Optimization, the GenAI library fuses these operations. Instead of reading 4-bit converting to FP32 multiplying, it often performs the multiplication directly in the compressed domain where possible, saving massive amounts of memory bandwidth. Let's discuss the role of C# features in AI architecture. In this specific context, C# features are not just syntactic sugar, they are architectural necessities. Now, let's talk about idisposable and the using statement. Concept reference. In Book 5, we discussed resource management in .NET. Application, AI models are heavy resources. A model object in ONNX GenAI holds pointers to unmanaged memory, native C++ buffers. If we rely on the garbage collector, GC, to clean this up, the memory might not be released immediately, causing an out-of-memory exception on edge devices. Implementation. Here, we're immediately instantiating 2 critical components for our local LLM inference, the model and the tokenizer. Notice the using keyword. This is a crucial C# construct for managing unmanaged resources. In the context of LLMs, especially those based on native libraries like GGUF models, memory management is paramount. The using statement ensures that dispose is called automatically when these objects go out of scope, releasing the underlying native memory. Without this, we'd risk memory leaks, especially in long-running applications or if these objects were frequently created and destroyed. This is a best practice for deterministic resource cleanup, preventing resource exhaustion and improving application stability. We are loading a model named Llama 3-8B Q4.GUF, which suggests a quantized version of the Llama 3-8B model, indicating a trade-off for reduced memory footprint and faster inference at the cost of some precision. This is crucial for edge scenarios where you might load/unload models dynamically based on available battery or thermal constraints. Now, let's explore span T and memory T. Concept reference. In Book 4, we explored high-performance data processing. Application. When passing input text, prompts, to the model, we must convert strings to token IDs, integers. Standard string manipulation creates many temporary objects on the heap, triggering GC pauses. In real-time inference, e.g., a voice assistant, a GC pause of 50 milliseconds is noticeable and breaks the flow. Implementation. Here, we're making a crucial architectural decision by using read-only span int for token IDs. This isn't just a stylistic choice, it's a performance-driven one. By using span T, we're able to work directly with a contiguous block of memory, typically on the stack or a segment of an existing array, without incurring the overhead of memory allocation on the heap. This is particularly vital in high-performance scenarios, such as tokenizing input for an LLM, where every millisecond and every byte of memory counts. Allocating new arrays on the heap for each tokenization operation would lead to increased garbage collection pressure and potential performance bottlenecks, especially under heavy load. By using spans, we treat the prompt as a contiguous block of memory, aligning perfectly with how the ONNX runtime expects input tensors. Moving on to record types for configuration. Concept reference, immutable data structures. Application, configuring a model, temperature, top P sampling, max tokens, requires a structured approach. Using C# record types ensures that configuration objects are immutable once passed to the inference engine. This prevents accidental modification of generation parameters during the inference loop, which could lead to non-deterministic behavior. Here, we define a C# record named generationConfig. This is a relatively new feature in C#, introduced in C number 9, that provides a concise syntax for creating immutable data models. Notice how we're using positional parameters with default values, temperature equals 0.8f and max tokens equals 128. This means that if a caller doesn't explicitly provide these values when creating a generationConfig instance, these defaults will be used automatically. This is a powerful way to ensure that our generation parameters always have sensible fallback values, making the API easier to use and less prone to errors. The immutability of records is a key architectural choice here. Once a generationConfig is created, its temperature and max tokens cannot be changed. This promotes thread safety and predictable behavior, especially in concurrent environments, as we don't have to worry about one part of our application modifying the configuration while another part is using it. Let's discuss theoretical foundations. To understand the loading process, we must understand how the loaded model is used. The inference loop relies on the KV cache, key value cache. Analogy, the conversation thread. Imagine a conversation. You don't reread the entire transcript from the beginning every time you speak. You hold the context in your short-term memory. The KV cache is the model's short-term memory. When the model loads, the cache is empty. As tokens are generated, the model computes the key and value vectors for each token and stores them in the cache. The loading implication: when we load a GGUF model, we must also allocate memory for this cache. The size of the cache depends on max context length. If we load an 8K context model, we must reserve memory for 8,192 tokens layers hidden dimensions. The sequence of operations: 1. Initialization, the model class loads the GGUF weights. The tokenizer loads the vocabulary. 2. Prompt processing, the prompt is tokenized. The model runs a forward pass for the entire prompt sequence to populate the KV cache. 3. Token generation, the loop. The model looks at the last token and the KV cache. It outputs a probability distribution, logits, for the next token. A sampler, temperature, top K, picks the next token. Crucially, this new token is appended to the KV cache, and the process repeats. This diagram visualizes the iterative generation process, where each new token is appended to the KV cache and fed back into the model, tracing the data flow from the GGUF file on disk through the C# boundaries to the final generated text. Now, let's talk about edge case considerations in theory. When designing the loading mechanism for edge devices, several theoretical edge cases must be accounted for. 1. Partial model loading. What if the GGUF file is larger than the available RAM? The system must utilize memory mapping, as discussed, to stream weights. However, this introduces latency if the storage medium, e.g., SD card, is slow. The theoretical solution involves prefetching, loading the next layer's weights while the current layer is computing. 2. Quantization mismatch. If the ONNX Runtime GenAI library expects a specific tensor layout, e.g., Q4_K_M, but the GGUF file uses an older quantization method, e.g., Q4_0, the loader must either fail gracefully or attempt a runtime conversion, which is computationally expensive. The loader strictly validates the header to prevent this. 3. Endianness. GGUF is strictly little endian. When loading on edge devices that might use big endian architectures, rare, but possible in embedded systems, the loader must perform byte swapping. C# binary reader handles this implicitly based on the system architecture, but it's a critical theoretical point for cross-platform compatibility. Now, let's talk about theoretical foundations. Loading GGUF models in C# is not merely a file operation, it is a complex orchestration of memory management, data decompression, and graph execution. It leverages the GGUF format for efficient storage of quantized weights, the ONNX Runtime GenAI for optimized execution, and C# features like idisposable and span-t to manage resources efficiently on the edge. By abstracting the heavy lifting into the GenAI library, C# developers can focus on the application logic, handling user input and processing output, while the runtime handles the mathematical heavy lifting of transforming compressed weights into intelligent text. This architecture ensures that even resource-constrained devices can run sophisticated models like Llama 3 and Phi-3 locally, maintaining privacy and reducing latency. Now, let's explore basic code example. This initial block of comments serves as a high-level introduction to the purpose and context of the code. We're setting the stage for understanding why this example is important, especially in the realm of edge AI. Notice how we immediately highlight the local inference aspect, line 4, and connect it to real-world scenarios like IoT devices, lines 9 to 10. This emphasizes the core architectural decision, running AI models directly on the device rather than relying on cloud services. The implications are significant: enhanced privacy, reduced latency, and offline operational capability, which are critical for many edge deployments. We're also introducing the specific technology being used, ONNX Runtime GenAI for GGUF models. Here, we're outlining the essential prerequisites for running this code successfully. This is crucial for anyone trying to replicate the example. Specifying .NET 8.0 SDK, line 15, tells us the target runtime environment. More importantly, we identify the Microsoft.ml.ONNX Runtime GenAI NuGet package, line 16, which is the bridge between our C# application and the underlying ONNX Runtime GenAI library. This library provides the necessary bindings and functionalities to load and execute GGUF models. Finally, the requirement for a downloaded GGUF model file, line 17, is a practical instruction, highlighting that the model itself is an external asset that needs to be acquired, not something generated by this code. This separation of concerns, code versus model weights, is standard practice in ML deployments. These are the using directives, which are fundamental in C# for importing namespaces. Notice how we bring in system, collections, generic, system.io, and system, threading, tasks for general-purpose functionalities like console output, data structures, file operations, and asynchronous programming. The most critical import here for our specific task is Microsoft.ml.ONNX Runtime GenAI, line 26. This is the external library that provides all the classes and methods we'll use to interact with the ONNX Runtime GenAI engine, enabling us to load models, tokenize text, and perform inference. Without this specific using statement, the core functionality of this application would be unavailable. We begin by defining our namespace edge AI local inference, line 28, and the program class, line 29, which is the entry point for our console application. The main method, line 31, is declared as static async task main, string, args. The async task return type is important because language model inference, especially token generation, is an inherently asynchronous operation that can take time. By making main async, we can use the await keyword later, allowing the application to remain responsive and not block the main thread during potentially long-running operations like model loading or token generation. The initial console.writeLine, line 33, simply provides a friendly welcome message to the user. Here, we're defining the path to our GGUF model file, line 38. This is a crucial first step in any ML application that uses a pre-trained model. We've hard-coded the file name Phi-3 mini for k instruct q4.guf for simplicity in this example. Notice the comment on line 36, which suggests that in a real-world application, this path would likely come from a configuration file or command line arguments. This is a best practice for making applications more flexible and easier to deploy without code changes. We're making an assumption here that the model file will be located in the same directory as the executable, which simplifies deployment for a basic example. This block implements a fundamental error handling check, verifying the existence of the model file, line 40. If the file is not found, we immediately provide clear feedback to the user, lines 43 to 46, instructing them on how to resolve the issue. This is vital for a good user experience and robust application design. Without this check, attempting to load a non-existent model would result in an unhandled exception later, which is much less user-friendly. We use console.foregroundColor to make the error message stand out, a small but effective UI detail for console applications. This check ensures that we don't proceed with expensive operations like model loading if the primary resource is missing. We introduce a try-catch block, line 49, which is a critical C# construct for handling exceptions and ensuring application robustness. Inside the try block, the first significant action is initializing the model object, line 54. Using var model equals new model path, is a very important line. The using keyword ensures that the model object, which likely holds unmanaged resources, like memory allocated for the model weights, is properly disposed of when it goes out of scope. This prevents memory leaks. The model constructor takes the GGUF file path and is responsible for loading the model's weights and architecture into memory, preparing it for inference. This is where the bulk of the model's data is loaded, which can be a memory-intensive operation, especially for larger models. Following model initialization, we move to initialize the tokenizer, line 59. Just like the model, the tokenizer is wrapped in a using statement for proper resource management. The tokenizer is absolutely essential for any language model. Its role is to bridge the gap between human-readable text and the numerical representations, tokens or token IDs, that the model understands. The tokenizer constructor takes the model object as an argument because the tokenizer's vocabulary and rules are typically embedded within the model's metadata, especially for GGUF files. Without a correctly initialized tokenizer, we wouldn't be able to feed input to the model or interpret its output. We then define our prompt, line 62, which is the natural language input we want the LLM to process. Here, we perform the crucial step of tokenizing our user prompt, line 67. Tokenizer.createStream, line 66, creates a stateful tokenizer stream, which is particularly useful for decoding tokens one by one later, allowing for streaming output. The tokenizer, encode, prompt, call converts our natural language string into a sequence of ulong, unsigned long, integers, where each integer represents a token ID. These token IDs are the actual input that the language model will process. We then print the user prompt and a message indicating that generation is starting, lines 69 to 70, and set the console color to green, line 71, to visually distinguish the model's output. This section is about configuring the generation parameters, which significantly influence the quality and style of the model's output. We instantiate generatorparams, line 77, using our model object. Notice generatorparams.setSearchOption, max_length, 200, line 78. This sets a hard limit on the total number of tokens, input plus output, the model will generate, preventing endlessly long responses and managing computational resources. GeneratorParams.setSearchOption, do_sample, true, line 79, is also very important. It enables stochastic sampling, meaning the model will choose the next token probabilistically rather than deterministically picking the most likely one. This introduces creativity and variability, making the output less repetitive. Finally, GeneratorParams.setInputSequences, tokens, line 80, feeds our tokenized prompt into the generator, setting the initial context for the model. We initialize the generator object, line 85, which is the core component responsible for the iterative process of text generation. Similar to model and tokenizer, it's wrapped in a using statement for proper resource management. The generator takes both the model and the generator params we just configured. It essentially encapsulates the state of the generation process, managing the current sequence of tokens, the model's internal states, like KV cache, and applying the specified sampling or greedy search strategies. This object will be used in a loop to produce tokens one by one. This while loop, line 88, represents the heart of the inference process, the token generation loop. While generator.isDone is the condition that keeps the loop running until the generator signals that it has completed its task, e.g., reached max_length, generated an end-of-sequence token, or encountered another stopping condition. Inside the loop, generator.computeLogits, line 91, is where the heavy lifting happens. The model takes the current sequence of tokens, processes them, and outputs logits, raw, unnormalized scores for every possible next token in the vocabulary. Immediately after, generator.generateNextToken, line 94, applies the configured search strategy, e.g., sampling or greedy decoding, to these logits to select the actual next token ID. This two-step process is fundamental to how autoregressive language models generate text. Within the generation loop, after a new token ID has been generated, we need to retrieve and decode it. Ulong, next token IDs equals generator.getSequence, 0, line 99, retrieves the entire sequence of generated tokens up to this point for the first, and in this case, only, sequence. We then extract the very last token from this sequence using next token IDs, _1, line 100, which is a convenient C8 feature for accessing the last element. This next token ID is a numerical representation. Crucially, string next token equals tokenizer stream, decode, next token ID, line 103, converts this numerical ID back into a human-readable string. Finally, console, write, next token, line 106, prints the token immediately. This immediate printing creates the illusion of streaming, making the output appear as if the model is typing it out in real time, which is a common and desirable user experience for LLMs. Once the generation loop completes, meaning generator.isDone, return true, we reset the console color, line 109, and print a completion message, line 110. This provides clear feedback to the user that the process has finished. The catch, exception X, block, line 112, is vital for gracefully handling any unexpected errors that might occur during model loading, tokenization, or generation. If an exception occurs, we catch it, print an error message in red, lines 114 to 115, and then display the stack trace, line 117. This detailed error reporting is invaluable for debugging and understanding what went wrong, especially in complex systems involving external libraries and large models. Without this, the application would simply crash, providing little diagnostic information. By scanning this code you can go to the website with more details and with buying options. On leanpub.com you can find the discounted bundle with all the volumes. This lesson is excerpted from Volume 9, Chapter 7 of the C# and AI Masterclass ebook series and from the volume Edge AI and Local Inference. Running LLMs, Llama/Phi, locally with C# and ONNX. You can find all source code here, https://github.com/edgarmilvis/C# programming series. The ebook includes 20 chapters, each one with diagrams, advanced examples, and 5 exercises with solutions. Subscribe to the channel to watch more videos. Thank you for your attention. I look forward to seeing you in the next lesson.